morning. I am here again for my course Aircraft Stability and Control. Today I am in lecture number 50. This lecture belongs to the tutorial number 10, that is Numerical Problem on Dynamic Stability. I am Dr. Yagya Dutta Dwivedhi, Professor from Institute of Aeronautical Engineering, Hyderabad, India. From last few months, I am taking the class of Aircraft Stability and Control. In this course, I have discussed about aircraft static stability for longitudinal motions, that is called the longitudinal static stability. Then I have covered the lateral and directional static stability. Then we have done sufficient work for aircraft equations of motion in 6 degree. Then we have solved the equations of motions by using perturbed theory. And finally, we have done our classes for dynamic stability. We should understand first what is the static stability. The static stability is the ability of the aircraft, once it is disturbed and the disturbing force is removed, the aircraft is tending towards its equilibrium condition. If this condition is met, we can say that aircraft is statically stable. Once we talk about the dynamic stability, in dynamic stability, if the aircraft is disturbed, after disturbing, how much time it is taking to regain its equilibrium position, how much frequency and how much damping is there, these parameters are important for dynamic stability. But for the static stability, we are not concerned with time factor. We are only concerned with if it is disturbed, and after disturbing, if you remove the disturbing force, the tendency of aircraft is whether it is trying to come to its equilibrium or initial condition or not. That is the intention. So we have done this for longitudinal case, and we have seen that for the longitudinal case, horizontal tail plays a very important role for making aircraft statically longitudinally stable. Because we know that to have the static stable, two conditions have to be met for longitudinal static stability. First condition is Cm0 should be greater than 0. So if the Cm0 is greater than 0, then we can trim the aircraft as positive angle of attack. If we are not able to make Cm0 sufficient positive, then it is very difficult for aircraft to trim for positive angle of attack. If your aircraft is not able to trim in positive angle of attack, then the controlling ability or the pilot response will be nowhere. So control will be ineffective. So we want that some effectiveness should be there in the aircraft so that we can make the aircraft stable. So you can see this here. This is the aircraft, and here is the one CG and the AC. If the AC is behind the CG, this will try to make the aircraft nose down. So here Cm alpha is negative, but Cm0 is also negative. So both cases are not good. So just I am drawing here first initial case. This is the aircraft. Okay, this is the wing. This is here CG, and here is AC. If like this, then there will be lift here, lift, and this will try to make aircraft nose down, CM, negative, or nose down. So if this is the aircraft and AC is behind the CG, this force lift will make aircraft nose down. But here CM also will be, CM naught also negative. So if I draw this plot here, CM versus alpha, so this plot will go from here to here, like this it will go. Okay, so CM is, alpha is less than 0 and CM naught, this is also less than 0. But I don't want like this. I want the CM should be positive. CM naught should be positive. It should start from here and then it should go like this. So this is the trim point. And this trim, this is called alpha trim. This alpha trim should be always positive for any longitudinal static aircraft. So how we will get? If most of the aircrafts, they are this CG will be CG of the aircraft and this is the AC. Always this lift will be like this. CM will be generated. CM alpha will be positive and CM not also positive. But how we can make this CM alpha as a negative? For that we have to add a tail here. So this tail, if you make the negative setting angle, it will generate lift like this LT, and this LT into this small LT, LT into a small LT will make in this direction, and that is called CM naught positive. So this tail will make this CM naught positive. So that is the beauty of this aircraft, that the tail plays very important role, and in this tail setting angle, tail volume ratio, are the main component which contribute towards the aircraft longitudinal static stability. So in this class, I am going to take some numerical problems related to the dynamic stability of the aircraft. In this, we are going to discuss about following questions will be answered. Understand the concept of the phugoid and the short-term mode. These things I am going to discuss. So this is the problem, the numerical number 1. The alpha by delta E transfer function for a T-37 cruising at 30,000 feet and 0.46 Mach follows. Find the natural frequency, damping ratio, damped frequency, and time constant for the short period and phugoid modes. Okay, so these equations are here given, and alpha by delta E is also here given. So we have to find out the omega n. What we have to find out? We have to find out the omega n, then damping ratio zeta, then damping frequency omega, and time constant we have to find out by the help of given equation. So this equation is given here, and this you can see that it is a minus 0.0924 s plus 336.1. Another is s square plus 0.0105 s plus 0.0097. Here we have the two equations, two polynomial equations. Here s square plus 4.58 s plus 21.8 s square plus 0.0098 s plus 0.0087. So these equations are given. Now we are going to solve this equation, and how we are going to get it is explained in this problem. So the solution of this numerical is, we have the equation as given in the problem. So here we have alpha by delta E is equal to minus 0.0925 s plus 336.1 in one bracket, another is s square plus 0.0105 s plus 0.0097 divided by s square plus 4.58 s plus 21.6. Another equation is s square plus 0.0098 s plus 0.0087. So now we know that these are the characteristic equations. We go immediately to the two characteristic equation. These are the first equation is this, and another equation is this. So this is the first equation, and this is the second equation of this characteristic equation. So we have written here s square here plus 4.58 s plus 21.6, and this equation we have written here s square plus 0.0098 s plus 0.0087 is equal to 0. Now we have to compare this by s square plus 2 zeta short period, then omega n short period s plus omega n square short period. SP indicates the short period. SP indicates short period. And you know that what is the meaning of short period? If I disturb from here like this, no problem, within no time it is vibrating like this. So just I will again explain. The short period means aircraft is flying and you have disturb like this, it will do like this and come. Within fraction of second, it will come to its equilibrium position with a fast oscillation. Oscillation will be there, but very fast and quick, and it will come to its equilibrium position. This type of condition is called the short period mode. So now we have to solve these equations, and we have to find out omega n and zeta. So if we find out that if we compare this, the first equation, so in this, if you see this omega n square is equal to 21.6. So here omega, here I will see omega square n short period is equal to 21.6. So omega n sp is equal to under root 21.6, and this will give 4.65 radian per second or hertz. Okay, so this we got for omega n for this first case, or for the first characteristic equation. Now if we want to find out the second characteristic equation here, so here what is there? Omega n, this for the second case, is equal to under root here 0.0087. 0.0087. So we are going to get here 0.0933 radian per second. So for the second characteristic equation, the vibrations are very, very less. So if we make it like this, you will go like this, 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 then you will be getting. So this is called the long period or phugoid. It is a phugoid case. So like this, we have to find out the frequency. If the frequency is high, it means it is very highly vibrating and it is coming down to its equilibrium position. Now we can find out the first characteristic equation as being for the short period mode because of the higher natural frequency. So how we can get that it is short period or the long period? If we compare the two natural frequency. So for one, the Fugate dynamics are contained in the second characteristic equation. So we know that omega n sp is equal to 4.65 radian per second and omega n ph is equal to 0.0933. So it is very quick, okay, and it is very slow. So if I draw a plot for first case, this is omega n. So it will go like this, And if you take for the second case, it is a Fugate, pH. So if it is disturbed from here, it will go like this, 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 and it will go. So it may take some 15 to 20 seconds. The aircraft will take. But here it a friction of second. It will take friction of second to come for the short period mode. And it is a long period or the Fugate mode. It will take sufficient time to reach to the its equilibrium position. That we have to understand. And this is the dynamic stability. So if your longitudinal case, we have the short period and the long period. And by seeing the equation and their omega n of the cases, we can find out that it is an oscillatory motion because we are getting the this roots, two conjugate roots, and this root shows that it is a vibrations and it is a oscillatory motion. And if the frequency is high, that is called the short period, and if the frequency is very low, then it is a long period and it is called the Fugate. Now if we compare the zeta, if you see here that in this zeta is equal to what? If you see 2 zeta omega n is equal to 4.58 and 2 omega 2 zeta sp omega n is equal to 0.0098. So from here we can get that zeta short period is equal to 4.65 divided by 2 omega n. So here 4.58 divided by 2 into 4.65. So you will get 0.493 here. So the damping ratio is 0.493. But here if you see 0.0098, so here 0.0098 divided by 2 into omega n Fugate. So how much we got the omega n Fugate is this. So here 0.0933. So we get 0.0525. So this is the damping ratio. And if you see, it is a nearly 0.5 and it is a 0.05. So it is a 10 times. In short period, the damping is 10 times higher than short period. Okay, so that is why if you see here in this again, if I draw like this and you are disturbed from here and it is, you see, like this, but in this like this. So it is a long period. Here this zeta is very less, 0.0525, and for this case it is a 0.493. Okay, so this is called the short period and this is called the long period and it is also called the Fugate. So in this way we can find out that whether it is a short period or the long period, and we can calculate like this. Now we have to find out some other parameters. Those parameters are also very important to understand the concept of dynamic stability. So notice that both the short period and the forward responses will be second order of zeta, and is less than 1. Both responses are stable because zeta omega n is positive for each mode. So both are the stable because this zeta and omega n are positive. Okay, we are not getting the negative. If we are getting the omega n and zeta, both are the positive, then both are the stable case. So in this way, we can find out that whether the aircraft is dynamic stable or not. Now we have to find out the damped frequency or omega n. So this omega d, this damped frequency is omega d. So omega d is equal to omega n under root 1 minus zeta square. Okay, so omega d, we can SP means short period is equal to omega n of short period under root 1 minus zeta square of short period. So we will get here 4.65 under root 1 minus 0.493 whole square. So after solving, we will get this value 4.046. Initially, we got 4.65. It is a natural frequency, but here little less. It is called the damped frequency. So after damping, we will get this much 4.046 radian per second. If you see about the forward mode or long term, so omega n forward 1 minus zeta square forward, omega n we have received 0.0933 under root 1 minus 0.052 square, and this we have got 0.0932 radian per second. So we got these four values: omega n, zeta, omega d, and zeta for omega d for the short period, and for the forward mode we have got. Now to find the time constant, tau for short period is equal to 1 by zeta sp omega n sp. So 1 by zeta sp we got 0.493 and omega n sp 4.65. So we got this value this much second. It is taking this much second to come to its equilibrium position. But if you see for the forward, this is taking 204.2 seconds. So if I draw these two items like this, for this case, that is SP. I am drawing the plot for SP, and it is just this is. Okay, so it is a 0.436 second. But if I draw for this is the, okay, this is 10 second. Now, this is the 100 second, and here is the 200 second. So it will start from here, go like this, it will go like this, it will go like this, slowly, 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 it will come like this. So this is called the forward. This is called forward mode, and both are stable case. Okay, because we are getting all values, we are getting positive. If we are getting omega n, zeta, tau sp, tau ph, if we are getting the positive value, it means they are stable. But if the values are, time values are very, very high, it means it is a forward mode, and it will take 204.2 seconds. It means nearly 4 minutes. It is taking 4 minutes to come to its equilibrium. And you know that aircraft speed is very high, so it is not advisable to have like this. It will take so much time, like this. So it is not good. So these are things we have to consider. Now we have completed a very nice example of one of the problem in which we have find out that what is the natural frequency and what is the damping ratio and how much time it is taking to stabilize the aircraft. Now, in the next also, it is very much related to that part, and you will see that the aircraft is stable in dynamic stability. To have the dynamic stability, we have seen that omega n zeta should be positive, and also we have to ensure that it is a short period mode or the Fugard mode. We don't want much time to take for the aircraft to come to the stable condition. So we should make sure that the damping should be sufficient so that it should reach to its equilibrium position without taking much time. That we have to ensure. Now we have the second numerical problem. In this, find the time response for the following system. In this, the one system, the equations for the x double dot plus 10x dot plus 16x is equal to 32. The conditions are given here. X at 0 condition initial is 0 and x dot also 0 at the 0. Okay, so rate also 0 and starting point also from the 0. Means the distance is also 0. So here we have this second order equation, and we know that to find out this omega n and zeta, applying the general form of second order differential equation, x double dot plus 2 zeta omega n x dot plus omega n square x is equal to omega n square y. This is the equation, and from this we have to find out that here omega square is equal to here 16. Okay, so if you compare from here to here, so what we got? Omega n square is equal to 16. So omega n is equal to under root 16, and this we will get 4 radian per second. So we have got the omega n. Now we have to see that this parameter. So this we have to compare with this and this. Okay. So here we got 2 omega n is equal to 10. So 2 zeta omega n is equal to 10. So this zeta is equal to 10 by 2 omega n. So 10 by 2 into 4. So it is 5 by 4. So you will get how much? You will get 1.25. So here this it is given 1.25. So we got this zeta or the damping ratio. So we got here damping ratio zeta is equal to 1.25 radian per second. Okay, so this is we have got this equation. So now here there are few conditions which we have to satisfy because here we got zeta is equal to more than 1. We know that the solution is of the form of case 1, means 2 real unequal root. Okay, so here we got case 1. In this 2 real unequal root, therefore we need to solve for the roots. So P12 is equal to here minus B plus minus B square minus 4AC by 2A. Okay, so here minus 10 plus minus under root 10 square minus 4 into 16. So we got here minus 5 plus minus 3 is equal to minus 2 and minus 8. We got this 2 root. So here both are the roots are the negative, but we want the negative only. Okay, so the homogeneous transient solution is x t is equal to c1 e to the power minus 2t plus c2 e to the power minus 8t. All this value we have to put here, and we have to put this 8 here. This is the solution for this transient problem. To find the steady state solution, xss t is equal to a. So in that, if you put here a double dot plus 10a dot is equal plus 16a is equal to 32. So here this is equal to 0, this is equal to 0. So we will get a is equal to 2. So we got a is equal to 2. So we then have xt is equal to xsst plus x trans t is equal to 2 plus c1 e to the power minus 2t plus c2 e to the power minus 8t. So now the first condition, we have to put x at 0 is equal to 0. So 2 plus c1 plus c2, and at x is equal to t is equal to minus 2 c1 e to the power minus 2t minus 8 c2 e to the power minus t. So x dot 0 is equal to 0 minus 2 c1 minus 8 c2. So c1 is equal to minus 4 c2. So 2 minus 4 c2 plus c2 is equal to 0. So this c2 is equal to 2 by 3 and c1 is equal to 8 by 3. So this value we have to put in the previous equation, and this we can get the time response because xt is equal to 2 minus 8 by 3 e to the power minus 2t plus 2 by 3 e to the power minus 8t. This response has two time constant. So this tau 1 is equal to minus 1 by t1 is equal to minus 1 by minus 2 is equal to 0.5 second. And this tau 2 is equal to minus 1 by t2 is equal to minus 1 by minus 8. So it is a 0.125. So this you can see that the second case is very less. So if I draw here time, so first case it will take more time, but the second case it is taking less time. Okay, so this you can say it is a short period, and this is the first case is the phugoid here, and this case is short period. Okay, so like this we can understand, and we have to see that these things are working properly. Now this problem you can do in your home. I have given here. You can note down and try to solve this problem in your home assignment. This will be good to do in your home. Okay, so try to solve this problem and understand it is like this same type of problem is there. Just I have given that you should also try from your side so that you can understand the real problem of this stability. So we have seen that in this, the first case is 0.5 second and another is 0.1 second. So it takes 5 seconds to, it is going like this, 1, 2, 3, 4, 5. But the second case is disturbed. Okay. Very friction of second, 0.1 second it is taking to come to its equilibrium position. So by this time factor, we can understand that if the time is taken more, it takes a lot of time. Aircraft will go like this, like this. It is called forward. And if it is less time, if it is disturbed, it will come to its equilibrium. So mathematics, you should also mix with the physics. Try to understand the physics of that mathematics. Then only you can become a good engineer. Otherwise, it is just solving a mathematics and just you forgetting it. If you are engineer, you should have the concept of mathematics is very, very essential, but try to understand the physics of that derivation or any equations which you have derived. What is the physics of that problem? That also is very, very essential to understand. So I'm going for the next numerical, the numerical number 3 for the today's class. And here it is related with the Eulers angle. And we know that, what is the Euler angle? We know that the Newton's laws of motions are applicable for the inertial reference frame. For the aircraft in atmosphere, we assume that Earth is the inertial frame, and we assume that Earth rotation is constant, and we can take Earth as a inertial frame. The axis system which belongs to the Earth is called the Earth axis system. Once aircraft is flying, the aircraft experiences the body axis system. The body axis system, pilot is sitting, towards his nose is the positive X body axis, towards his right hand. Okay, just I will show you. Okay, this is the aircraft. Pilot is sitting at the center or above the center of gravity of the aircraft. Towards the nose of the aircraft, it is a positive X body axis. Towards the right wing of the pilot is a Y body axis, and towards the earth it is a ZB or Z body axis. Once aircraft is flying, aircraft is experiencing the body frame axis system. However, whatever derivations we are solving by the Newton's laws of motion, they are applicable from the earth axis system. Earth is very far away from here, and we need some formulation that how this system can give a better understanding to each other. For example, pilot is flying on the aircraft, he is sitting on the cockpit. ATC is 400-500 miles from the aircraft, and if you relate with these two by the Newton's law, it is really very difficult. How the pilot will know and how the ATC will know what is the speed of the aircraft. It is really the acceleration, the distance, the velocity of the aircraft, and other parameters, your attitude, your angles of attacks, your yaw, pitch, all other parameters, both should have the same data. If aircraft is flying the really 500 miles per hour, ATC people should also experience that yes, aircraft is flying 500 meters per hour. If you see that you are traveling in the air, in the train, and you are lifting a ball, so your friend is on the platform and your train is moving, your friend will not feel as what you are feeling. Your friend will feel that it is going like a parabolic, but it is for you, it is going and coming, it is straight, in your hand it will come. So when there is two reference or different, then it is very difficult to get the same feeling. And in olden days, 30-40 years back, so many accidents are happened due to this misunderstanding of altitude, velocity, and other parameters, and aircraft used to collide. Mid-air collision have taken place. So after that, they have put the devices so that aircraft itself will decide if any object is nearby. So like this, many accidents happen, and now due to induction of the computer, due to induction of the ILS, instrument landing system, due to induction of the flight management system of the computers, all type of sensors, aircrafts are very, very safe now. And aircraft itself, even autopilots are there. These autopilots can sense that there is any aircraft nearby to me, and autopilot will take appropriate action and try to avoid any incident or accident. So how these things are happening? It is the issue here. We know that Eulers angles are there. If you want to convert from one axis to another axis system, we have to rotate the aircraft in such a way that a proper sequence. If you want from earth axis system to body axis system, first you have to psi. It is a towards the earth axis, towards the, this is the positive psi. First psi, then theta, pitch. After pitch, it is roll. So first angle you have to turn the yaw, then another is a pitch, and then it is a roll. So phi, theta and psi. Psi, theta and phi means yaw, then pitch and then roll. Okay, phi should be the last. So in this sequence you have to do, and these angles are called phi, this psi, theta and the phi are called the Eulers angle, and these angles are very useful to determine the position of the aircraft with respect to the necessary conditions. So here we have the one problem. The aircraft has the following Euler angles and Euler rates. So Euler angles are this. These three are the Euler angle and these three are the Euler's rate. Okay, means per unit time. Okay, these are the, and these are the Euler's. So find the roll, pitch and yaw rate, that is PQR. Explain result with practical consequences on airplane. Okay, so these are the parameters which are given to you, and by these parameters we have to find out the roll rate P, pitch rate Q, and R is a yaw rate, and explain its physics. I told you that doing mathematics is one issue, but understanding the physics is a great achievement. As we are engineer, you all are going to be the aeronautical engineer, and this is very much essential for any aeronautical engineer. You know that other branches, other than this topic, your colleague branches, mechanical and other people, they study the same thing, but these parameters only you are the person who study this thing. So here given is psi is equal to 0 degree, psi dot is equal to 10, theta is equal to 0 degree, theta dot also 0, phi is equal to plus 90 degree, and phi dot is equal to 0 degree per second. So we know that the pitch rate P is equal to minus sine theta psi dot plus phi dot, and Q is a, so if you see here, it is P is a roll rate, Q is a pitch rate, and R is a yaw rate. So roll rate P is equal to minus sine theta psi dot. So here P is equal to minus sine theta is equal to 0. You see here it is 0 into psi dot is equal to 10 plus phi is equal to 0. So sine 0, 0, this you got the 0. Now to find out the Q, Q is equal to sine psi cos theta sine phi cos theta psi dot plus cos phi theta dot. So here Q is equal to sine phi. Phi is how much? 90 degree. So sine 90, then cos theta is equal to 0, then it is a 10. Psi is equal to 10 plus cos 0 into 0. So here sine 90 is equal to 1, cos 0 is equal to 1 into 10 plus 0 is equal to 10 degree per second. So your pitch rate is 10 degree per second. Now we have to find out the yaw rate R. So this yaw rate R is equal to cos phi cos theta psi dot minus sine phi theta dot. So here you will get cos 90 is equal to 0, 0 and 0, and sine 90 is equal to 1 and 0. So you will get 0. So we got here P is a roll rate is equal to 0 degree per second. Pitch rate is 10 degree per second and R is equal to 0 degree per second. So these are the answer. So here note that for this flight condition, a 10 degree per second Euler yaw rate. Okay, here 10 degree yaw rate psi dot is felt by the pilot as a 10 degree per second pitch rate. You see, very nice result. If you do the yaw rate, you do the yaw rate of 10 degree, pilot will feel a pitch rate. That is the difference. Just I told you, from the earth axis system to body axis, pilot will not feel what the people on the earth, they are feeling that the ATC, the person who is in ATC, he is feeling that aircraft is yawing 10 degree per second. But the pilot, he is feeling that it is pitching. That is why you have to understand very well the physics of the problem. Okay, so next problem is here. An aircraft has the following Euler angles: psi 0, psi dot 0, theta 0, theta dot is equal to 20, and phi is 90 and phi dot is 0. So find the roll pitch rate. In the same way, the practical consequences. So here the results are, you will get P is equal to 0 degree per second, Q is equal to 0 degree per second, and R is equal to minus 20 degree per second. Note that for this flight condition, a 20 degree per second Euler pitch rate theta is felt by the pilot as a minus 20 degree per second yaw rate. So if you are pitching in the earth axis, if you are pitching like this and this is minus towards the left, so pilot is feeling that aircraft is going towards the left side. That is the difference between the earth axis system and the body axis system. Okay, so I think this problem we have already done. Okay, thank you very much for joining and hope this is understood to you. If any problem, I have given my email here. You are welcome to ask any question. Thank you very much for
like, share and subscribe. Hit the bell icon for more updates.